everyone, today we're going to be talking about Cellobiase. So first we're going to be looking at a special organism, which looks like this. This is a fungus known as Aspergillus niger. It is commonly known as black mold. The reason why we're looking at this organism is because it produces a special enzyme called cellobiase. As its name suggests, cellobiase is able to break down cellobiose, which has a structure that looks like this. Cellobiose is a carbohydrate formed by two glucose molecules, and therefore it's a disaccharide. Since it's formed by two glucose molecules, we can call it a sugar. However, it's not the type of sugar people can consume. Since cellobiose is found in plant matter, it's derived from cellulose. Cellulose is found in things such as wood. Humans do not have the enzymes that can break down wood and cellobiose and use it for nutrients. Therefore, people cannot consume plant matter, and we cannot consume cellobiose. The way how cellobiase works is that cellobiose will bind to its active site like this, and then through enzymatic reaction, cellobiase will break down cellobiose into two molecules of beta glucose. Once we obtain beta glucose, it can be further fermented into ethanol. Ethanol is a biofuel which is renewable. As a renewable source which does not require excavating, it is better for the environment, and it is a good source of energy. But first, how do we go from wood to ethanol? First, we have to start out with the cellulose. Structurally, cellulose looks like this. It has very compact molecules which aid in the rigidity of plants, such as trees. However, as stated earlier, cellobiase can only act on cellobiose. Therefore, we need to break down cellulose into smaller molecules. First, using treatments such as heat, acid, ammonia, or other treatments, we break down cellulose into individual strands, like this. Then, with the help of other enzymes such as exocellulases and endocellulases, we are able to break down the strand into cellobiose. As explained earlier, cellobiose will react and bind to cellobiase and break down into beta glucose, which can then be fermented into ethanol.
We learned previously that cellobiose, a disaccharide, is broken down into two glucose molecules by cellobiase. But how do we study the activity of cellobiase? We study the activity of cellobiase, specifically the kinetic activity of cellobiase, using a Cellobiase assay. Now, what is the purpose of this assay? The ultimate goal of this assay is to determine the Vmax and Km of cellobiase. Vmax tells us the rate at which cellobiase forms products, and Km tells us the affinity cellobiase has for its substrate. So to perform this assay, a set concentration of cellobiase will be mixed with differing concentrations of P and G. These mixtures will then be added to a 96-well plate in different wells at different time points. These wells will also contain a basic solution, also called a stop solution. This solution not only stops the reaction from proceeding, but it also turns any product present yellow. These experimental reactions can then be compared to standards, which contain known concentrations of product in stop solution. Once the reactions and the standards are prepared in the 96 well plate, this plate can then be put into a plate reader that is set to measure spectrophotometry at 410 nanometers. The plate reader will then provide a raw data Excel file. This raw data will have all the absorbances from both the standard solutions and from the experimental reactions.
Hello everyone, my name is Carlos, and today we're going to be going over the Cellobiase Assay. The most important thing to do first is to grab our materials. So we're going to need our 4 test tubes, empty test tubes, our 4 stock solutions of PNG, our Cellobiase, our stop solution, and last but not least, our 5 tubes with PN standard. So each test tube listed before are going to have different sets of concentration. We're going to start off with our empty test tubes that are going to be filled with Cellobiase later on, and those concentrations are going to be 0.125 millimolars, 0.25 millimolar, 0.5 millimolar, and 1 millimolar of PNG. Our PNG stock solutions are going to have concentrations of 0.188 millimolar, 0.375 millimolar, 0.75 millimolar, and 1.5 millimolar of PNG. And our last set of solutions, which are going to be our PN stock, are going to have 0.0 nmoles, 0.0 nanomole, 6.25 nanomole, 12.5 nanomole, 25 nanomole, and 50 nanomole of PN. Alright class, so we're going to start off using Cellobiase. We're going to transfer 150 microliters of Cellobiase into each of our 4 empty test tubes. From there, what we're going to do is we're going to use our stop solution, and we're going to transfer 50 microliters of our stop solution into the wells that we're going to be using on our 96 well plate. These wells are going to be represented using black circles. And last but not least, we are going to use our PN standards, our 5 test tubes of PN standards, and we're going to transfer 50 microliters into each of the bottom wells in row H. We're going to use our PNG stock solution, and we're going to transfer 300 microliters into our Cellobiase solution that we pipetted before. And from there, we're going to take our new mix, and we're going to transfer 50 microliters into each of the appropriate wells at certain time intervals. Our first transfer is going to be at 0 minutes, followed by 1 minute, 2 minute, 4 minutes, 10 minutes, and 20 minutes. So our plate should look like this by the end. Okay, so once all the solutions have been added to the 96 well plate, we're going to come over here to the plate reader. We're going to set up the plate reader to 410 nanometers, and then we're going to press our little eject button, open up our plate reader, place our 96 well plate onto the plate reader, and then enter it in, and then press read in order to read the plate. So the formula y equals mx plus b that we're going to get from our previous graph are going to give us y being the absorbance, which would be our data for the PNG, and x being our concentrations of PN nanomole. If we manipulate the equation, we'll get an equation of x equals y minus b over m. we can look at our other graph that we had with all of our other data. And from there, we're going to insert our y and solve for x via this method. Once we've plugged in all of our previous data into our new formula, we're going to end up with a new set of data. This set of data is going to be used in order to determine the rates of reaction for cellobiase in the presence of our different substrates. We're going to go ahead and plot that into a scatter plot, which is going to go ahead and give us the rate of reaction, and we're able to go ahead and calculate a linear formula for this. M is going to be the most important variable of this and will be used in the next step of the experiment. We're going to go ahead and take the M from our previous linear formula, and we're going to plug it into a new table where we're going to have the concentrations of P and G. We're going to use this to create a Michael-Menten curve. So we're going to go ahead and plot it onto a curved scatter plot, and we should get a graph that looks similar to this. So then what we're going to do is we're going to take the reciprocal of each of our data, and we're going to go ahead and plot it into a new graph, which is going to look like this, a Lineweaver's-Burke graph, where we're going to take that graph and we're going to go ahead and place a trend line, and from there we're going to go ahead and take the linear formula. Yay! We're almost done. In order to solve for Km, we will use the same equation. However, this time when y is equal to 0, mx is going to be equal to negative b. Therefore, x is equal to negative b over m. And to solve for Km, all we have to do is place our new x underneath negative 1. So therefore, we should have x in the denominator and negative 1 in the numerator. In order to solve for Vmax, we simply use the equation that we got from our Lineweaver-Burke graph, and then set x equal to 0, so that way y will be equal to b. So then our equation for Vmax will be Vmax is equal to 1 over b. Well, that reaches the conclusion. We have finally solved for Km and Vmax using the Lineweaver-Burke graph. So, we're finally done. Woo! That's it, everyone. See you next time.